Okay, so I'm really very pleased to be here in Rome. So on behalf of the CepC Accelerator team, so I report to you the completion of CepC Accelerator CDR and also R&D towards TDR. So the title of this kind is the first appeared in my talk before. So this is a really historical meeting, the first one in outside of China. So I will not to go through all these line by line, but you'll see I try to make this talk as heavy as possible, as complete as possible, but as quick as possible also. So this is thanks Franco, so I skip this. So I remind you that this is the minimum, the requirement for the luminosity both for Higgs and for Z. So this is 10 to 34. That means we stick to it, but remember this number in order to understand our alternatives. So otherwise you got lost. Many people make this kind of misunderstanding. So this I skip. So I briefly to give you. So we finished this one, and we finished the progress report last year, in the middle of last year. And also at the end of last year, we almost finished the draft. And this year, we will print in July. So for the moment, we're editing this CDR, and also with appendix. So the appendix is very important. So I will also include my talk of the content of the appendix in the talk, in the last part of the talk. So to understand CepC as a system, whole system, you can remember, you can buy these 5 systems. So the injector, linear injector, the booster, and the collider ring, MDI. So I put it here connected with detector, and also civil engineering. So in this case, in these 5 domain, I will give you so-called the content of this CDR to show you what is the status. So this is important also to show you how we evolve from the beginning pre-CDR to the CDR. And also you will understand why the parameter is like that. And so in fact, my feeling for the CDR, we can reach CDR is in the September of 2016, when we're doing, when we are doing this one. So finally, we decide with the CDR, we take this full double ring case, and also we keep this advanced partial double ring as alternative. So we focus on this. So this one is the CDR machine is like that. That means for the Higgs and for the Z and W, the 3 energy, they can work with same hardware, only RF including. So this is the injector. So if you look at this parameter, you will find the luminosity of Higgs about 3. And the Z about 16, and if the main content is at all these field level is the 3 Tesla, but if we reduce to 2, we have potential to go to 32. So this is the result of the CDR. That means for the collider ring, we reach the design goal. I mean, this is the summary. For the booster, we reach the design goal. This all becomes green. And also for the injector also. So to prove that all these tables has been works to support it, so I give you the detailed description of all these systems. First is a collider ring. So the collider rings like that, a little bit complicated. This is just to show you that for H mode, we use all RF to have a high energy, and for the W and Z, we just make a switch. I mean, the same machine, but you just switch the passage of the beam. In this case, the machine can work at the 3 energies without changing any hardware. So this is the lattice in the interaction region, which is the most different from existed circular collider. Never a collider like that exists. So this is a new one. So about the arcs, so because this two beam line, I mean a double ring, so we have this dual dipole and the quadrupoles. And for RF region like that also. So I will not stick to that. So this is the whole one. So the whole ring, you have everything, so including injection. So so this is the beam simulation just to test, to show that you can reach your luminosity and you can have a good lifetime, and also what is the necessary dynamic aperture you need to design this machine. So this is, we do it through beam simulation. So for example, this is the design and also the simulated one. I will not stick to that. So so for the requirement of the aperture, so after you have the lattice, and after you made beam simulation, and then you know what the dynamic aperture you need to guarantee all these. So this is the, how to say, the requirements, and for different things, for the Higgs, W, and Z. So we know where, to which level we have to reach. So for example, this is for the 3 cases, and this is reached. I mean, what we have reached dynamic aperture. And by that, we say that we completed the CDR, that means we reached the goal. If you remember 2015, and then we have 0 dynamic aperture for single ring with a Priso schema. So this is the fundamental difference of the CDR and the pre-CDR. It works now. So we leave something not yet fully studied. We don't include it in the CDR as a criterion to say that this is a criterion to complete CDR is error. So we put this, we are working on that. We are talking about that in the CDR, but there are many works to do, so we can leave after CDR. We continue to do that. So this is something, and for the RF system is very important because this is 2G GeV machine, but it is this machine, the RF is the heart of, I mean, the motor of your collider. So this one you have very carefully designed, and with you know what is the requirement. For example, this is you need 240. So this amount of cavity is relatively small. It's not very big. So this is the design of the cryo module. So I have 6 cavities. I mean, each cavity you have 2 cells, and so I will skip all these things, and how it's implemented in the tunnel parallel to the main tunnel. So the collective instability is very important, especially for Z. So we have the vacuum chamber, you have all the impedance, and you have all kinds of instabilities, single and the multi-bunch, and longitudinal and transverse, and many, many things. So you have to analyze your emittance budget. So all these things has been done, and we calculate all the threshold of for the different machines, and also So these kind of things like a police to say that whether your hardware is good to be accommodated with your beam parameter, with current, and with your luminosity. So this is a hard limitation, is for example for Z. So for the LINAC injector is not something very, how to say, but it's conventional. Here is a conventional. I will show you some new things, but here is a conventional. But it can reach the designed value by these schemes. So we have a damping ring here. So I just show you the proton, the electron LINAC, proton LINAC, how the beam, how they gain energy from to the 10 GeV. So this is damping design. So we complete, with that, we complete almost all the system. I did not show the transport line from LINAC to the ring, but we have the design that also. I did not put it here. So this is the booster now. We're going into the booster from LINAC to the booster, and this is the booster design to the 10 GeV. But the start from 10 GeV means your dipole field is 30 Gauss. So we have to solve that problem. I will talk about that later in the hardware and the new injector scheme. So this is booster extraction. And this is the booster design, which is 100 kilometers suspended on the roof of the, just above the collider. And that aperture is good. So there is no much a big surprise for these kind of things. So we have two ways of injection, on X, off X. And so surely if we make it on X, so the dynamic aperture requirements for the beam dynamics will much loosed. So we studied the two kinds. So this is the time structure, at least the one of that. And this is for the kickers. So both booster injection, extraction, we have kickers, septum, and kickers. All the parameters are there. So all the machines are connected. So this is the booster RF, which is a 1.3 gigahertz RF, the same as ILC, so the same technology. So the reason why we did not put into RF. So later I will show you R&D. We don't put too much stress on these. So this is the 1.3 gigahertz RF, like that. But the Q is very high. I mean, it's so this we need niobium doping or infusion. So for the MDI, it's very important also. So I put here all the important parameters, L star 2.2. And so the separation of your quadrupole at 2.2, in fact, the same as FCC. And in fact, this is the same as a Super K. So this is 6 meter, something like less than 7 centimeter. So this is your technology limit now. So I put here all the detailed information about MDI, so you can look at it later. For example, the QD0, QF1, all the field, the strengths of the field, I mean the length and everything. So we put into this parameter. So MDI is a system. So this is the detailed design of MDI with quadrupoles, and many lifetime connected phenomena. So at least here we listed several, 4. And we calculated the key things, these 4, which is lowering the lifetime by of the machine. So all these things is higher. So about site, for the moment, I think now with all this is not means we will stop to do that. But at least with this number and this distribution, we cover almost all the possibilities in China. I mean, around center is Beijing. You have north, south, and left, and right, and so we have almost everything. And especially the first 3, we have. So Xiaoyu she will gave a detailed report in the parallel session. So, for example, this is Funing design. So we make exercise on this site. And all the civil engineering, so we made a complete one, so we know how much it cost. So how you implement in this example site. About the power of this machine, so the beam power, radiation power is 30 megawatt. So for Higgs, it's less than 3. We pressed a lot and make many optimizations. So if you remember, the ILC 250 is 110 megawatt. So here is less than 300 megawatt. You can compare. But luminosity is different. One is 1 IP, 1.5, 10 to 34. Here is 2 IP. Each IP is 3, 10 to 34. So about the Z, so Frank Zimmerman always asks me about the Z power, so we prepared also for Z power here. So this is the cost breakdown. I did not put the absolute value, but you can guess if you have some experiences. Anyway, we give you the proportional. The first one is including the civil cost. So you will find the civil cost is big. And another one is the cost without including the civil engineering. So in this case, you see the magnets and vacuum chamber really take a big amount of money instead of RF like IOC. So the RF is very small, about 6%. It's very small. So alternatives. So I showed you the advanced partial double ring scheme. The reason why we use that scheme is we try to limit the cost of the machine. So instead of a real two ring, it's a partial double ring, so about 30%. In this case, the parameter, you cannot use the first parameter for the CDR. The reason why, because you cannot reach. What you can reach is the Z. It's a 10, it's 1. This is a 1 10 to 34. That is the upper limit for the advanced partial double ring because you cannot put too much bunches there. So this is the, for example, this is the bunch structure. The problem is the sawtooth effect because this is not a two ring. So you have sawtooth effect, and this limits your dynamic aperture. So that is the reason why this machine, if it works, the optimum luminosity is 1 10 to 34. So that means that if we stick to this as a minimum, so we have two options. One is advanced, another is CDR, I mean baseline. One can be higher, another is the upper limit. So this is the relation. So some people, when they say that, they cry, they make, say, why you. Imagine if we put the lower limit to higher, so there will be any alternatives. So we cannot. So this is some explanation to you. So this is RF, also important RF. This is complicated, many beam loading calculations. So this is the advanced partial ring beam loading calculation. You have energy the drops and also phase shifts. So all these things you have to check carefully. But for the moment, all these RF is okay. So the dynamic aperture is ongoing because this is not the key thing for the CDR. So we just put it in the appendix. To solve the problems low field, later we have a high precision dipole, but we have a new idea to use plasma to increase energy. Instead of 10 GeV, we can increase energy to 44. So just to Z. So this is something so Wei Lu and his representative will give a talk in this parallel session. So this is something interesting, and I think in this workshop, for the first time, he can give a quite complete design of this one, satisfy the goal. So this is very important message from him. So for the polarization, for the CDR we don't have, but in the appendix we have. So that means we will work on that. So nicotine, Sergey, he will give a talk in parallel. So we put this on the appendix, and this chapter was written by Professor Sergey Nikitin in collaboration with BNP. So about the EP also, this is included in the, this is a far future, but we included in the appendix. So about R&D, so this is, I talked too much about RF, so I just skip to these things. So this is something fabricated, and this is design, model, and this is fabricated, but the far future, not in this design, we don't use it. But anyway, we built it. This is a pre-CDR cavity. So about the cavity, we took cell cavity, already reached the goal of CEPC. So this is the recent results in May 11. Also for the niobium doping, we see the Q raised, but due to no EP, so this is bad. And in the end of this year, we have EP, and then we can make this higher. So this klystron, we are working on 3 kinds of klystron, from the first one, second one, and the third one. And this one have higher luminous efficiency. For the first phase, we're working on these now, right now, and the construction is underway. So we're just we are working on this direction. So also we are trying to working on this large cryogenic system. This is a very big one. For the many magnets, so we have to work on these magnets. So you see the number of magnets. So more than 70% of the tunnel was occupied by the magnets. So this is so-called the booster low field 30 Gauss dipole. 2 options. One is a high precision one to see whether this works. Another one is air coiled. So that means this is surely it works, but maybe power, you need the electric power. But anyway, this something can guarantee it works. So the vacuum chamber, as I said, it's really very expensive and also critical for the Z, yes? So this is something. So I did not cover all the R&D, but this is the key R&D. So about CIPC, this is the Industry Promotion Consortium and Industry International Collaboration. So we have this last year established this collaboration, and all these people represent the key companies of China related to CEPC and SPPC. For example, this is some advertisement from the company, and they are working on for XFEL, and they are working on SLAC LS2, and also IGP company built I don't know what kind of magnets for the last several decades. And also the material company and the cavity company, they are bidding, they can build for that, even contribute to IOC later. And also these for the machine to underground drilling machine. So China is now can fabricate all kinds of this kind of drilling machine, and the largest diameter is more than 13 meter. So the international collaboration, we have many MOUs. So different laboratories working on these domains in red, and also many meetings, including this first one, is very encouraging. So I put Hong Kong here. This is not dedicated to CEPC, but CPC people goes to this Hong Kong neutral meeting quite regularly, and it's a good platform. So for the IOC, we have a good collaboration, and there's a good synergy, and we have a long time with ATF2, the cavities, and the power source, I mean klystrons and the kickers, and so we have this collaboration. So the last transparency is China New Scientific Policies, which is quite new in the beginning of this year. And I think if you read carefully, all these things is really correspond, I mean, to CPC. So also international collaboration. So I will not read line by line, but I think this page gives you the political envelope. I mean, it covers CPC, LHC, IOC, and many things if you read these sentences behind. So the conclusion is, so we have a complete CDR on time for the accelerator part. And also the siting and engineering implementation progress well. Hardware design and the key technology R&D goes well with financial resources. Also international collaboration with industry progress well. The young generation, all I presented the material has been done, I mean, mainly by the people whose the age is around 35 or even less. So CPC has entered a new phase started from this workshop. So I think this workshop is very important. It's a historical workshop. So we are entering a new phase. Of course, there are many design work should be refined, but we can focusing quite strongly on R&D to make it, that means to make this machine work in reality. So finally, the government policy is quite a good guarantee, I mean, political guarantee in general. So thank you for your attention, and thank you for all the teams and the international collaborations. So thank you very much.
Thanks, Jie. Questions?
Thank you for this comprehensive review. Indeed, my question is, did you estimate the extra cost if you go from 2 IPs to 4 IPs like?
Never.
Never?
Never. We never do that, but it's easy, I mean easy. We know scalings, but it's easy. But we never, I mean, in the strategy, we put 4 IP as CP, never discusses even like alternatives, never. But never one also.
But looking at your table, it seems that will be a fraction of the total, right? Because the main cost is the civil engineering and magnets, right? So in principle, should not have a big impact on the total budget, just to change the number of IP. Am I wrong?
I did not really follow your question.
No, looking at your table, your graph about the cost, it seems that the most important costs are civil engineering, right? And then yeah. I guess it's just the machine build-up that is quite long. So yeah, changing the number of interaction points should not have a big impact. It should be some order of 10%, 10, 20 more, right?
Very good question, because in this this is no detector included. This cost.
I see. Okay.
This cost no inductor, but anyway, you know the cost of 2 detectors is compared with this one is small, very small.
Okay.
Hello. I have a question. In the cost for the detectors, yes. Were the caverns for the E plus E minus detectors, or were also foreseen for the PP collider detectors?
No. In this phase, even the tunnel, we have no inclusion of any, how to say, the cost element, except the length of and the width of the tunnel. So including these into, otherwise no.
But the cavern would have to be redone for the proton collider.
No, but for the cost here, we have we calculate only 2 experiment holes. Right. We did not calculate the holes for the 2 IP hole for the PP. Right. Yeah.
Also, if the beams are separated before the collisions with this butterfly or so, that includes bigger tunnel.
Exactly.
In this area.
Exactly.
That is included.
Yeah, all these things has been designed. Xiaoyu, she will show you the detailed interaction region, which is very wide. And,
okay, thank you.
I'd like to follow up on the earlier question about 4 IPs.
Okay.
In addition to any cost, isn't there some implication on the beam and therefore the luminosity if we add more IPs?
Exactly.
So that's not just a cost, so it may be...
Sure.
Yeah.
Imagine, it's very easy to understand this. Imagine you have infinite IPs. What happens? You have 0 luminosity. Yeah. To give you the ratio is the lumina. I mean the beam parameter scales with the square root inversely an IP. So you understand. So if you put an IP into infinity, you have 0 luminosity. So it's not independent. So if you put the beam, so beam is getting stronger. You have this is,
Okay. Other questions? Bill, you wanted to do a question? No?
I was wondering how you saw the political ramifications of the Japanese decision on the ILC that should come this year.
I cannot solve that problem, but I would say that if I ask my personal opinion, so I representing the people, I fully happy that and wish IOC could have a good positive at the end of this year. The reason why that these two machines are totally different. They start from the same starting point. One go to the EE TV. Another is SPP as destination. And the two technologies are totally different. As I said, the CPC, we include only 2 GeV of less than 3 GeV superconducting cavity, accelerator. So this kind of machine never push this kind of technology, but this machine, I did not talk to these. We are working on superconducting magnets, ion-based. So CPC, SPC, we're pushing the magnets, superconducting mag technology to a very high level. And this one is go to the IOC, go to the, yeah. So these two machines technology will have a big application to vast. So they don't collide. And so it's a really good thing. If IOC has a bad news for Chinese project, we don't think we receive a good push for us.
Question.
It's not a question, it's a comment. I'm not quite sure that by the end of the year there will be a decision by the Japanese government concerning ILC.
No, what they do is something. What is sure is they have to say something. This is for sure. But to say yeah, no is one answer. Another is yes is not to say oh we do that. It's yes we start to negotiate with other countries. So
they are saying this since several years.
Because never Japanese government say that. But they have to say at the end of this year. Yes.
The previous one was the last question.
Yeah, could you comment on the timeline for a Chinese decision instead? We saw 2020 for the first down selection to 5 projects or so.
Yeah.
And then the final projects get selected later, I understand, but
yeah,
how much later?
Sorry, I'm afraid I don't have time, so I did not explain this important thing to you. So this sentence says that China, this sentence comes from these, you can find Chinese in the web on this statement. What he says is that till 2020, China will select 3 to 5 to support, R&D, yes. Imagine. And then at the end of, 2020, they select 1 or 2 into the real construction. We don't know, this will be CPC, maybe CFTR, the Chinese ITER, imagine.
Yeah.
But in my mind, this is just for free discussion, okay. So in my mind, maybe one is CFTR, which is the same order of magnitude of money than CPC, and another is CPC, so 2. Okay, but someone will say the other. But the hat is big, so I don't see now at the moment which project in China has this big hat to have this fit this hat. This is 2 things I saw have the same order of magnitude of money for these.
But the date for that second decision is still 2020, or?
Yeah, around this 2020. And there's another sentence, maybe it's long, I did not include, is that after that, we will select a bit more, 6 or to 10 projects to make it mature, and then, so this is much longer. So we are talking about something CPC connected pipeline.
Okay, thank you.
Thanks. Let's thank the speaker
Thank
again.
you.